Now let us go to the main flow sheet. We will close it down. Okay. So first is fix the streams. One is methanol stream and another is lactic acid stream. So we'll go to, okay, first let us bring in the model. So this is the batch separation model. Okay. And so this is the first charge. This is the pot content. And this is the distillate. Here we have two inlets. One is for methanol, another is for lactic acid. So we shall put in another feed over here. This one we will say the feed, or we will call it charge, and we will call it methanol feed. Okay. This one we'll call pot outlet, and this one we'll call distillate. Okay, so naming is complete. Now methanol is charged at 1 kilomole per hour, 80 mole percent at 25 degrees centigrade. So methanol input at 25 degrees centigrade, 1 atmosphere pressure, 1 kilomole per hour. Okay, so we will put it over here, 1 kilomole per hour. Okay, so this is our methanol. But no, methanol is not fully 1 kilomole per hour, it is 80 mole percent. So we will put it over here, 1 kilomole per hour, and mole fraction we will put it over here 0.8, and rest is water. Okay, so that's how it makes 80 mole percent of methanol. And now fix the charge. Charge is lactic acid 70 mole percent, 5 kilomole per hour at 20 degrees centigrade. So it is 20 degrees centigrade, 1 atmosphere pressure, 5 kilomole, and mole fraction, it is lactic acid 0.7 and this is 0.3. So that makes us 70% mole fraction of lactic acid. And both are at 1 atmosphere pressure. So our streams are fixed. Now we have to specify the block. Go to setup. In the setup, first set the process as pot of 1 meter dia and 1 meter tantan length. So first we have to set it as pot. Okay. Now this pot is having 1 meter dia and 1 meter tantan length. Then we have to use 4 kilowatt of jacket heating with total initial charge of 10 kilomole, where pad gas is methanol. Now For that, first we have to go to the, okay, before that we have to fix the reaction. Streams are not to be fixed over here because it is pot charge. Go to reaction and set the reaction 1 because we have painstakingly made that LHHW reaction, so we will use it. Go to heat transfer, and the heat transfer we have to put the jacket heating, and the jacket heating we have to specify the heat duty, which is 4 kilowatt. Okay, so heat transfer is set, and initial condition. So we have to place the initial condition. For initial condition, it is said that total initial charge of 10 kilomole where pad gas is methanol. So here, pad gas. What is pad gas? Pad gas is the component to be used as inert when initial condition is empty or initial charge. So let us use methanol as pad gas. And total initial charge is 10 kilomole. Okay. Now we have to set the operating step. Now the operating step includes changing methanol flow rate at 1 kilomole per hour at 0 ramp time, and stopping the batch as soon as lactic acid fraction goes below 0.01 in the pot. So there are two things that has been mentioned over here. One is the operating step includes changing the methanol flow rate at 1 kilomole per hour at 0 ramp time. So first add the operating step and describe the operating step as feed methanol flow rate, which is methanol molar flow rate 1 kilomole per hour. Okay, 1 kilomole per hour at 0 ramp time. Okay, so the operating step includes changing methanol flow rate at 1 kilomole per hour at 0 ramp time. And second condition is stopping the batch as soon as the lactic acid fraction goes below 0.01 in the pot. So what is the stopping criteria? Stopping criteria is the process variable. Which location? Pot. What is the process variable? Process variable is the lactic acid fraction. So the liquid mole fraction of component lactic acid goes below 0.01. Okay, and approach from above, because in general the lactic acid charge is 70%. Okay, and we are expecting it to go beyond 0.01, so it is approaching from above. So that's exactly what we are putting over here. So like that, all our conditions are set. Okay, now let us run the process. Okay, now the results are available. So let us see the results. You see the mole fraction. It has stopped at 5.10 hours. Okay. When did it stop? When the pot mole fraction of lactic acid at 0.009999. So just below 0.01. So as soon as the lactic acid mole fraction reached 0.01, it stopped. Okay, so this is the threshold. So time of batch start, it is 5 hours, and total amount of cumulative pot duty is 20 kilowatt hour. This is the liquid level in the pot. Total molar hold up, mass hold up, liquid volume, everything has been given. The temperature has been given, pressure is given over here. Okay, and vapor fraction also is given. The net duty is 955 calorie per second, which amounts to 4 kilowatt. Obviously, the pot 4 kilowatt duty has been given over here. Okay, so that is exactly what it is showing over here. Time profile is given over here. So as soon as it begins at time 0, and what happens immediately after time 0, and then as time progresses, how temperature, pressure and heat duty that changes. Okay, so it's time, pressure and heat duty profile, the composition profile and the hold up profile, everything has been shown over here. Okay, now let us go to the second problem. It says reconfigure the process as batch distillation column of 10 number of stages, but the reaction occurs only in the pot. Okay, the overhead of the column has one total condenser with total reflux. Initial condition is total reflux. The methanol is fed at 10th stage. One distillate receiver exists. The second to 9th stage have 0.01 kilomole of holdup. We have to reconfigure the process as batch distillation column. So let us choose it as batch distillation column. For that, we have to go back to setup, and instead of pot, we have to give batch distillation column. We'll press, and then what are the other things? The overhead column has one total condenser with total reflux. So it is total condenser with total reflux. Okay, so overhead column has one total condenser with total reflux, and it has 10 number of stages. So it has 10 number of stages, and reaction occurs only in the pot. Okay, and then methanol is fed at 10th stage. One distillate receiver exists. So we have only one distillate receiver. Go to the stream. Methanol is fed at 10th stage. Okay, it is at 10th stage. So we have to put 10 over here on stage 10. The second to 9th stage have 0.01 kilomole of hold up. So for that, the distillate receiver is having distillate at the product stream. Okay, so let us not calculate it from tray and packing hydraulics. Rather, we will specify over here condenser pressure. Let us keep it as it is, and we will put the second to ninth stage. So it is second to 2 and this is 9, and we'll put 0.01. Okay, right. So we are not complicating by asking them to calculate from tray or packing hydraulics at this point. So for that we have to provide the overhead condenser pressure, which we keep it as 1 atmosphere. We have to provide some column pressure drop, which we have given. By default, whatever is available we have given, and we have to specify the hold up that we had specified. Now we can run the process. Okay, so the run is complete. Now let us go to the results once again. Now here you find that it has stopped at 0.01, but it has taken 16.2392 hours of time. Unlike in the last case, where we have used only the pot type. Okay, in the pot type, we took only 5.1 hour of time in order to arrive at 0.01 mole fraction of lactic acid. But in this case, we took 16.2 hours of batch time when we have 10 number of stages. I mean, we worked it as with a batch distillation column rather than the pot. Okay, so let us see what other changes we have arrived at. The pot dynamics is almost the same. It's not changed. Okay, the pressure is a bit high over here. Last time it was 0.2 or something. Now it is 1.01 atmosphere pressure. The temperature is also higher. Earlier it was around 40 degree or so, but this time it is 91 degrees centigrade. We have got one distillate receiver, and probably that is the reason why it took more amount of time and some amount of material is going out of the system. Okay, so that is the reason the changes are being visible. And these are the profile results. We find the profile, temperature, pressure, heat duty, everything is visible over here. The composition at various stages we find over here. Okay. Now let us go to the last problem. It says reconfigure the process such that the pressure and hold-ups are calculated from packing hydraulics. Okay. So last time we avoided the packing hydraulics, but in this problem we are asked to use the packing hydraulics. So in this case we will not specify the pressure and hold up. Rather, we will calculate it from the packing hydraulics. So we will choose this button, and once we choose this, we have to go to the column internals, add new sections, add new section, start from second stage to ninth stage, use a packed internal column, and here we have packing section with 1 meter HETP and 1 meter diameter. So 1 meter HETP, 1 meter diameter. So not much information is given over here. So with this information, we'll run the process. Okay. So run is complete. Let us go to the results once again. Here you can find the batch time is not changed that much. Here the temperature has reduced a bit and the pressure is almost 1 atmosphere, or it is 1 atmosphere only. The heat duty also doesn't change, and the mole holdup has reduced a bit. We have not remembered the distillate receivers. Probably we have to run the other system once again to compare them. But let us see the profile results. Here also it is almost same because the pressure is same throughout. Temperature increases from 67 to 88. And we have insufficient data points to compare them. So best thing is we can take a screenshot of this result and go back to the previous problem, and there also we can take a screenshot and then compare both of them, which will give us a better way to compare how it has changed with different configuration. Okay. With that, we come to the end of this lecture. I hope you have enjoyed it. We'll come back with yet another interesting lecture very soon. Thank you.